Okay, then we will start our today's session. So good afternoon once again. Last class we have been discussing about this additive inverse, multiplicative inverse, and how we can able to find this additive inverse and all the people have been seeing, right? And we concluded with the extended algorithm to find the multiplicative inverse. So from this we can able to form a different sets. Like we already came across a set called Z, which denotes integers, right? Then we came across Z suffix n, which has called as a set of residues or have elements from 0 to n minus 1. Now I'm going to introduce a new set called Zn star. We call it Zn star, right? So in this one, it will have the elements. Okay, those elements have only the multiplicative inverses for this particular value of n. For example, if we take Z10, we have the element 0 to n minus 1, that is up to 10. Whereas Z10 star will have only elements 1, 3, 7, and 9. Because only these elements will have their multiplicative inverses existing. Other elements doesn't have multiplicative inverse. So if you have any Z suffix n and star, it denotes that the elements which are all present in this set will have the multiplicative inverses for them, right? So with this we'll conclude this modular arithmetic. Now we move on to the next one called algebraic structures. So till now whatever we just discussed, we saw what we mean by integers and other types of integers, modular operations, binary operations, other things. Now we are going to combine the set which we just saw till now, that is Z, Zn and Zn star, along with some binary operations. So with these combinations of set and the binary operations, altogether is called as algebraic structure. And these algebraic structures form a major backbone for our modern day cryptographic techniques. Right? Especially there are three algebraic structures called groups, rings, and field. And this field is a backbone of our modern day cryptographic techniques. And to understand this field, you should know what you mean by group and ring. Okay, so these are three common algebraic structures named groups, rings, and field. To start off with a group is also a set of elements. Okay, it will have a set of elements along with the binary operations. So in this binary operation, they will take either addition or multiplication. They won't go for subtraction, because if you take additive inverse, it will perform the subtraction part also. And for multiplication, we will be using multiplicative inverse, right? So we'll be having a set of elements along with a binary operation, which will be satisfying 4 properties. In below we can able to see 5 properties. Out of this, the 4 are compulsory. That is, first one is closure property. That is, if you have elements, like A and B, which belong to the set or group G, then A dot B, this dot can take either addition or multiplication, any one of the binary operation. Then the resultant value will also be the element in the set called G. Then we have associativity. If you have 3 elements A, B, and C which belong to the group called G, then A dot B dot C will be equal to A dot B dot C. And as I said, the dot is nothing but a binary operation. These 2 properties are compulsory. Then comes this is your third property called existence of identity. That is, if you take any element which belong to this particular set, there will be an identity element, okay, in such a way that if you perform the binary operation with the identity element and the element from the set will be ending up with the same element. For example, if you take addition, the identity element is 0. For multiplication, your identity element will be 1. So if you take identity element 0 and if you perform addition with A, it will be equal to A plus 0, which is nothing but your A. If you take 1, if you multiply 1 with A, it will be equal to A times 1, which will be A. So for addition, the identity element is 0. For multiplication, the identity element is 1 here. Then comes the fourth property called existence of inverse. That is, if you take any element A in this group called G, then there is always an element called A dash which will be inverse to each other. Okay, that is, if your dot is addition, A dash will be a additive inverse, and if a dot is multiplication, the A dash will be multiplicative inverse. So that if you if you perform the binary operation with this inverse elements, you will be ending up with the respective identity element. How in the sense, if you take addition, so we already know that A plus A dash is additive inverse will result in 0. We just saw this condition in the last class, right? Then if you take A multiplied with A dash, and you generally will take a mod. Without mod also you will be ending up with 1 as an output. And then 0 is nothing but your identity element of addition, and 1 is identity element of multiplication. So if this set of elements along with the binary operation satisfies this property of closure, associativity, existence of identity and existence of inverse, then I can able to call them as a group. Okay. Along with this four properties, if it satisfies this fifth property called commutativity property. Commutativity means if you have elements A and B, then A dot B will be equal to B dot E. Okay. Then I will be calling this particular group as an abelian group, or I can able to call this group as a commutative group. That is, if it satisfies the extra property of commutativity, then I can able to call the group as a commutative group or abelian group. Right. So, anyone have any doubt in this part? If it is clear, raise your hands. If you have doubts regarding this group, you can ask me. Or if you don't understand also, you can ask me. If you are clear, kindly raise your hand. Thank you, Venkat. Vijay Krishna. We'll see an example. I mean, this is a pictorial representation here. That is, the binary operation, whichever you take, will satisfy closure, associativity, existence of identity, and existence of inverse. Then I can able to call it as a group. The group will have a set of elements and operation. And along with this, if you have an extra property supported, then it can able to call them as a commutative group. So how this group can be represented? So group will be represented using this one, that is the brackets are in the format of greater and lesser than sign, and here comes a set of elements. Okay, here what they did in sense, the binary operation which they are going to perform is addition. So they took a set of residues as a set of elements. So set of residues obviously will have all the elements will have their identity inverse present in them. So inverses will be existing, identity element will be existing, associativity property will be also satisfied, and closure property will also be satisfied. Right. If it satisfies the commutative, then obviously the commutative property also satisfies. Because if you take any element for in the, assume that you have Z sets. If you take any element 0, 1, 2 up to 5. For example, if you take 3 and 5, and the addition is an operation, 3 plus 5 will be equal to 5 plus 3. So it is a commutative, right? And if, for example, if you're going with a multiplication operation, okay, there the set of elements will be Zn star, because all the elements which you're going to take should obey with the four rules. That is, inverses must exist. So if whenever multiplication comes into picture, I'll be taking the elements as a multiplicative. The set which has only the multiplicative inverses existing. Right. Now we come across a term called a subgroup. Okay. So directly I'll go to this one, so that will get a clear picture. That is cyclic subgroup. Thus, that is, if you have a group and the group has some elements, if I take each and every element in the group and raise it to a power in the sense from 0, 1, 2 and goes on, okay, I can able to form certain subgroups from that base, then I can able to call them as a cyclic subgroup. We will see what are the cyclic subgroups. For example, we have a group here G which has Z6 with addition as an operation. So can you people tell me what are the elements of Z sets? You can post in the chat box. What are the elements present in Z sets. So I need an answer for what are the elements for Z sets. I hope you get my question. I need an answer for what it will be Z sets, elements in Z sets. We got as 0, 1, 2, 3, 4, and 5. Right. Okay. One second. The elements are 0, 1, 2, 3, 4, and 5. Right. Now I am taking first element 0 and raising it to power 0. Okay. So here, since the operation is addition, generally if you in our school math, generally what we used to do in sense, if I write anything like 2 power 4 means you'll be going with 2 into 2 into 2 into 2. Okay. But here in this group, we are performing an operation of addition. So instead of multiplication, generally what we used to study in our school days, we will be performing an addition. So whenever I say any object risen to power 0, it means that I am not taking the value itself for addition. So the answer is 0. Generally anything power 0, we learned it to be 1, but here we'll be going with 0 since operation is addition. So I'll be getting 0 mod sets. So even if you take next element, like if you perform 1 power 0 mod sets, I'm not going to take this one for addition. So directly I'll be getting 0 as an answer. So no need to go for other elements or rise to the power of other elements. Now I'm going for the second element. Okay, that is number 1. So this is itself a subgroup called H1, because H1 will have element called 0 and addition as operation. And you can able to see this subgroup will also satisfy all the 4 properties. Right. Now I'm going for the second element. So 1 power 0, 1 power 1, 1 power 2, and so on. So if you go for 1 power 0, as I said, you'll be getting 0. 1 power 1, 1 mod 6 is 1. 1 square, you won't have multiplication here because we are going to take the binary operation as addition. So I'll be adding 1 twice. So 1 plus 1 is 2, 2 mod 6 is 2, then 1 power 3 is 3, 1 power 4, and 1 power 5. Can anyone tell why we can't go for 1 power 6 mod 6? Why we can't or no need to go for this 1 power 6 mod 6? I need response from your class, guys. The class is giving very poor response compared to your G1 slot. People who join later in the class, you can leave because I already taken attendance. Okay, any idea why?
So it is 6 only.
You'll get 6 answer. Sure. 1 power 6 mod 6. You'll be getting 6 mod 6. Answer is, what will be the answer?
0.
Yeah,
0,
0.
sir, 0.
0. So you'll be getting the same value here. If you go for 1 power 7, 1 power 7 mod 6, you'll be getting 7. mod 6, again we'll be getting answers 1. So it
1
will be repeating again. So that's why we are not going to increase the powers apart from this. So this subgroup, okay, is giving all the elements which are present in the same group itself. That's what is named as H4. H4 is equal to G. This is another subgroup. Now I'm going for 2. So 2 power 0, again 0. 2 power 1, I'm getting 2. 2 power 2, 2 plus 2 is 4, 4 mod 6 is 4. If I go for 2 power 3, I'll be ending up with 6 mod 6. So again I'll be getting 0. Then 2 power 4, I'll be going with 2 and so on. So here the 0, 2 and 4, this also forms a subgroup. In this example, it's termed H2. That is, we have elements 0, 2 and 4 under addition operation. It is also forming, satisfying all the 4 properties of the group here. Right. Go for 3. 3 power 0 is 0, 3 power 1 is 3. And if you go for 3 power 2, I'll be getting 3 plus 3 is 6 mod 6. Again, I'll be ending up with 0. Right. So, next one, this is nothing but your H3, the cyclic subgroup. And if you increase to the element of 4, 4 power 0 is 0, 4 power 1 is 4. 4 power 2 mod 6 is 4 plus 4, it's 8 mod 6 gives me 2. Again, it is the same cyclic subgroup H2, but only the elements position are changed here 0, 4, and 2. And for 5, you are getting the same elements from 0 to 1. This is the thing about your H4. Right. Right. Similarly, if you go for, how many of you have doubts in this cyclic subgroup with addition as operation? If it is clear, you can raise your hands. If you have doubt, you can unmute and ask. If it is clear, raise your hands. Okay, what about others? Is it fine? Now, similarly, if you go for your cyclic subgroup with respect to multiplication as an operation, here you'll be taking the group as Z10 star, right? So Z10 star, I hope you people remember the elements present in this Z10 star are 1, 3, 7 and 9. We already saw in the previous class. Okay, so here also I'm going to take each and every element. Okay, so 1, if we take 1, here 1 power 0, here you will go with a conventional mathematical way which we just studied, 1 power 0 with the multiplication. So anything power 0 is 1. So 1 mod 10 is 1. Next, the second element 3. So this one goes for my H1 subgroup. It satisfies all the properties of a group. Then we have 3 power 0 is 1, 3 power 1 is 3, and here 3 square is 3 multiplied by 3. And here 3 cube is 3 into 3 into 3. Right, 27 mods 10, 7, 1397. This is nothing but your H3, which is nothing but your entire group. And with respect to 7 also, we are getting the same subgroup, and with 9, we are getting another subgroup called H2. Right. So these many subgroups can be formed with multiplication as an operation and Zn star as a set of elements. Right. Now we move on to rings. Okay. So in ring, what we are going to do is we are just going to improve or enhance our group, because in group we'll be having a set of elements, that's no issue, but we can able to perform only one operation, that is you can able to perform an addition or multiplication alone, whereas in ring I can able to perform two operations at a time, that is addition and multiplication can be done over the set of numbers. So if you want to say the definition of a ring, I can able to define the ring from the group itself. So I can able to define a ring as an abelian group. So whenever I say abelian group, it is going to satisfy all the 5 properties, and the abelian group with addition operation. Okay, so if you're using addition operation, then it will be an abelian group along with the multiplication operation, which satisfies only these three properties. That is closure, associativity, and the new property this time is a distributive over addition. That is a combination of both addition and multiplication. A times B plus C will be equal to AB plus AC. Right. If these properties are satisfied by this multiplication operation, then I can able to call the particular set as a ring. Right. That is, your ring will have addition operation and a multiplication operation. So the addition operation will satisfy all the five properties. That's why it's called as an abelian group with additional operation. And multiplication will satisfy three properties, that is closure, associativity, and distributive property. If suppose multiplication is also supporting an extra property of commutative property, then I can able to call the ring as a commutative ring. Okay. Now further, still the multiplication is now is going to support some more property, like it is going to have an identity property. That is, some identity element is going to be there, and it has no zero divisors. Okay, then I can able to call this ring as an integral domain. That is, if you take a ring as a definition, from ring you can move on to commutative ring. From commutative ring I can move on to integral domain. Right. And the ring is formed from group alone, that is group with the addition as operation along with the multiplication with which satisfies the three properties. That is the group with the abelian group. Okay, this abelian group with addition as operation, multiplication, three properties. I can able to call them as a ring. Okay, so here you can able to see how the ring will be represented. So ring will be having set of integers altogether because it is going to occupy the entire set of elements. So ring will be represented like this with two operations of addition and multiplication. As I said, addition will satisfy all the five properties and your multiplication will satisfy only the three properties. Right. This will give a clear picture and yeah, distributive property. Yeah, right. That is, if the ring will be having set of elements and two operations. This is addition and this is multiplication. Addition will be satisfying all the five property. That's why they calling this one as a ring can be defined as a abelian group with addition as operation along with the multiplication which satisfies closure, associativity and distributive property. If it satisfies this commutative property, then I can able to call it as a commutative ring. Right. So how many of you understood this ring? Can you raise your hand? People who are not clear, kindly unmute and ask. Guys, if it is clear, raise your hands. If you have doubts, kindly ask me. At least one response. Sir, I'm not clear. Sir, I'm clear. Now we move on to field. Okay. So field will be a set of numbers. Okay. And here also we are going to perform two operations. Okay. So if you take a field, it will also perform addition and multiplication. Both addition and multiplication are going to be abelian group, but except one condition with the multiplication in the sense, we are going to ignore the number 0. We already saw while discussing finding the multiplicative inverse, 0 doesn't have multiplicative inverse at all. That's why they're ignoring 0 here. Okay. And this altogether make it as a ring under these two conditions. Right. So if you see, a field can be denoted as a commutative ring. So whenever I say commutative ring, it indirectly mean that I'll be having a abelian group with addition operation and multiplication with the 3 plus commutative group. Commutative property altogether is meant whenever I say commutative ring. Okay, along with this, the second operation will satisfy all five properties. Okay, defined for first operation, except that the identity of the first operation has no inverse. So what is this identity of first operation? First operation is addition. So what is the identity element of first operation? Can you people tell? Identity element of addition? Just now, 10 minutes before we discussed. Zero. Yeah, perfect. So identity element of the first operation has no inverse. So as I said, multiplication has nothing to do with find the multiplicative inverse of zero. So this is a definition of a field, that is we'll be having both addition and multiplication, both satisfying all the five properties, but except the existence of inverse, zero doesn't have inverse here, right? So this is the definition of a field. Want to put everything under a shell, that is group, ring and field, you can able to see, suppose you assume that group is using addition as an operation here. So this addition as an operation, it satisfies closure, associativity, identity and inverse. Okay, this one operation, then I can able to call them as a group, right? Right. Now I'm going to make that group as a commutative group. Along with this one, it is going to satisfy the fifth property called commutative property. Then I can able to call it as a abelian group. Right. Now this group is going to be extended to multiplication. Okay, in order to make it as a ring. So it's going to satisfy an addition property, sorry, addition operation with the abelian group. Along with this, the multiplication property satisfying closure, associativity, and distributive laws. Then I can able to call them as a ring, right? And along with this, if it satisfies the commutative property, the optional one, then I can able to call them as a commutative ring. That is, now I'm using that both operation, that is commutative ring will have addition with 5 properties, multiplication with the 3 plus this commutative property. Okay. If it includes multiplicative identity and no zero devices, then it is called as integral domain. Whereas field will include all, field will include addition with 5 properties, multiplication with all the 5 properties, right? Along with multiplicative inverse, except that zero element is omitted. Then it is called as a field. So this is how your group, ring and field are interrelated to each other. Okay, I hope the group, ring, field concept is clear. If everything is clear, can you raise your hand? I mean, whether group, ring and field, these three concepts, if it is clear, kindly respond by raising your hand. Okay, if you people feel that, okay, myself asking you whether it is clear, clear is boring, then I will just keep on going with the syllabus until you people stop for the doubt. Right, it will be easy, very easy for me to teach that way. Next one, we are going to see the finite field, which is also called as Galois field. This Galois field is used in our modern day cryptography techniques. Okay. What is this Galois field in the sense? The number of elements present inside that finite field or Galois field will be either a p power n number of elements, where p is a prime number and n will be a positive integer. So it will be represented as gf of Galois field of p power n. Okay. If n takes the least value as 1, we will be using Galois field of p. And if your p takes the least value of prime number, which is 2, we'll be using Galois field of 2 power n, which is most important in modern day cryptography technique. Galois field of 2 power n. Modern day cryptography lies on this Galois field of 2 power n. Hey. So here, if I say Galois field of p, it will have a set of integers, like how we have Zn. If n is equal to p, I can able to write it as the set p will be having elements from 0, 1 up to p minus 1. Okay, and it can able to perform the arithmetic operations of both addition and multiplication under the model of the prime number p. So here, for example, if your n is equal to 1, okay, you'll be having the set of elements Galois, I mean, as is 0 to p minus 1. Here is the most simplest Galois field is Galois field of 2. That is when n is equal to 1 and the p is equal to the least prime number 2. You'll be having only two elements, 0 and 1, where you can able to perform both operations of addition and multiplication here. The addition, we can able to see 0 plus 0 mod 2. So here the modulus is nothing but mod 2. That's why 0 plus 0 is 0 mod 2 is 0, 1 mod 1, 1 mod 2 is 1, and 1 plus 0 is 1, 1 mod 2 is 1, 1 plus 1 is 2, so 2 mod 2 is 0, right? And similarly the multiplication and inverses. For 0, the additive inverse is 1, for 1, the additive inverse is 0, and here for 0 we don't have any multiplicative inverse, but for 1 we have 1 as a multiplicative inverse here, right? So if you go for Galois field of 5, so that is general expression is Galois field of p power n. In this case, your n is 1 and your p is 5. So you have the 5 elements 0, 1, 2, 3, 4, right? And this is the addition table, multiplication table, and the respective additive and multiplicative inverses, right? So why is that we are discussing these things in the sense? Okay, before moving to this one, this is a summary of group, ring, and field and the respective supportive integers. If you take group, I can able to perform either addition or multiplication. I can't able to perform both at the time. If you are using addition, you'll be going with your Zn, and for multiplication, you'll be going with Zn star as a set of elements. And if you go for ring, you can able to perform both addition as well as multiplication. And here the supported set of elements is a set of integers. Whereas if you go with field, while implementing field, we'll be implementing them as a Galois field with the p power n. So it will be always using your prime number set p, and the modulo will also be a prime number. And here you can able to use both addition as well as multiplication here, right? Since here they didn't mention the division stands for your multiplicative inverse. Why they didn't mention for ring in the sense, if you're using set of integers, all elements doesn't have the multiplicative inverse here, right? So this is a nutshell of our, I can able to summarize how group, ring, and field and their respective supported operations and the supported set of integers. So the Galois field of 2 power n, okay, which is most used in our modern day cryptography. Why in the sense, if I take a Galois field of 2, whenever 2 comes into picture, the elements will be either 0 and 1 alone. If you take modern day technology, all the informations are represented in terms of bits, which is made of zeros and ones. Only how many bits going to make the data is our concern. So that this n will decide. For example, if I say Galois field of 2 power 2, okay, it means totally 2 power 2 is 4, totally 4 elements will be there, and each element will be made up of 2 bit, right? So in this one, 0, I mean either 0 or 1 alone will be there. 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 set of elements. That's why I stress that Galois field of 2 power n is going to be used in our modern day cryptography much. So to understand this Galois field of 2 power n, we should be clear of what I mean by polynomials or polynomial arithmetic and other stuffs. So is it clear regarding Galois field, GF, Galois field of 2 power n or Galois field? If it is clear, kindly raise your hands. If you have any doubts in this Galois field, kindly unmute and ask.